Thank you for the introduction. I'm Theodor Schnitzler. I'm with Maastricht University. And I'm presenting here today on behalf of Evangelos Bitsikas from Northeastern University, who basically led this project. But it's a pleasure for me to do this because the idea behind this work we collaborated on is very similar to something we've already been working on during my own PhD, which also initiated back then our collaboration for several years now, and that also includes Christina and Aanjhan. I'm starting with a brief introduction into SMS, which is some very fundamental technology in mobile network communication throughout all generations for, I think, more than 30 years now. And though we might be rather using Messenger app nowadays for communication, SMS is still something that is around, that comes along with all our phones we are carrying with us most of the time. So whenever we're sending an SMS, it first propagates to the mobile network base station we're connected to, and from there it goes to the core mobile network, to the SMS center. And as soon as it arrives there, it is forwarded to the receiver. Again, first to the base station the receiver is connected to, and then over the air to the device. And at the same time, the SMS sender issues a confirmation that the SMS has been sent. And once the SMS arrives at the receiver, they issue a delivery receipt back to the SMS sender and all the way back to the sender. We might be familiar with this from Messenger apps, with those check marks that come along with every message after we send them, but we are maybe not aware that this also exists for SMS. So when I'm now sending an SMS here from Philadelphia, depending on the receiver, whether it is one of my collaborators in Boston or a colleague back in the Netherlands, these messages and confirmations, they travel certain distances, and they differ, which means that there's the minimum time required for those to be exchanged also differs, which implies the presence of a timing side channel. And that one might be used the other way around in order to identify the location based on the observed time for those messages and confirmations to be exchanged. One important thing to know is that this timing connection only applies to the propagation and routing. Of course, in reality, this is more complex because there is also noise and processing at different stages at all those devices. That makes it a bit more difficult. So we've called this thing SMS-based location inference, and this works as follows. In the first step, we're sending lots of SMS to a certain target we're interested in, while knowing that this target is at a certain location. In this example here, at home. But we're not doing that only for one location, but repeatedly for different locations, while knowing they're at all those different places, for example, at work, at the gym, or some other place. Then we can analyze all those timing data we collected and generate fingerprints for either of these locations. At the final stage, we can then send more SMS without knowing where the target and where they currently are, and compare the observed times with the previous ones in order to identify the location out of the ones we know. That always works within the set of locations we know. And in this case, we would then detect that the target currently is at their work location. The problem with this is that there are many SMS being involved, particularly during the first phase of this attack. And the target might become suspicious when they're systematically receiving lots of SMS from us at all those different places. It is important to know that this also works with silent SMS. So everything happens without anything becoming visible on the device. So the SMS is sent, it is delivered, the delivery reports are exchanged, but the SMS is not showing up on the receiver's device. Yeah, let's have a look at how good this works out. We conducted experiments with targets in different countries. That works quite well, depending on the situation with more than 90% accuracy. We looked at different questions, such as distinguishing a specific set of countries, Or some binary problem, is the receiver in the same country as I currently am? And it's quite plausible that that could work between different countries because there are large differences in the distances depending on what set of countries you choose. But it also works for distinguishing locations within the same country that are considerably closer to each other. And again, depending on the specific scenario, I'm not really going into the details here because this is actually nothing new, but has already been presented by Evangelos at USENIX Security almost exactly 1 year ago. In this work, we changed a bit the focus of the analysis. We more systematically explored the position of the attacker. And we repeated all of this not once, but 3 times from 3 locations at the same time, and in order to compare performance between different locations, if they are consistent with each other, and to analyze how the attacker can improve their capabilities by coordinating multiple locations, by simultaneously attacking from different positions. And to explore this, we conducted measurements. They took place in 2 different areas, in Germany and the Netherlands. In those 2 clusters, they were roughly 130 kilometers apart. That's about 80 miles. In the Netherlands, there was 1 phone sending SMS from 1 location, and there were 3 locations for receiving SMS, one of which was also the sender location. And in Germany, there were 2 phones sending SMS in 2 neighboring cities, approximately 10 kilometers apart. So all these locations are in a very small area, quite close to each other. In total, we had in Germany 5 locations for receiving SMS, again, including also the sender's location. And for running the experiments and collecting all the data, we had a setup, which is the same as in previous work in the USENIX paper, but this time replicated 3 times at those 3 locations, 3 sending locations. We had 1 fixed device, sending device per location to send the SMS that remained consistent throughout the whole experiment duration. And on the device, we used a simple Android app providing basic functionality to send a silent SMS to a specific phone number that could be entered. And that app also then collected the timestamps for when the message was sent and for the 2 incoming receipts. The sending device was connected to a computer, running Python script controlling the phone through ADB, and the script iterated through those different receivers we were targeting and sent bursts of 20 SMS and stored the timestamps for the SMS, for the receipts, and that was repeated on an hourly basis. At minute 0, we sent SMS to receiver 1, at minute 15 to receiver 2, and so on. We had 4 different receivers that added up within the hour, so we could repeat every hour. We synced it through the 3 senders in order to measure all receivers, the same receiver at the same time. Therefore, we relied on the local clocks of the smartphones. We considered this fair enough to have the same conditions in terms of the network load when measuring those receiving devices simultaneously. In total, over the course of our experiments, we sent more than 260,000 SMS. For receiving SMS, I already said we had 4 devices. And those 4 devices systematically rotated through all the locations we had. 2 of the devices have been in all 8 locations, 3 in the Netherlands, 5 in Germany. And the 2 other phones have been in 4 locations. You can see that in the table. For the analysis, we extracted then, after collecting all the data, several timing features from the 3 timestamps, the moment the SMS was sent, the send receipt arrived, and the delivery receipt arrived. We calculated durations. The time to send the message, the time to deliver the message, and the overall time, which is the sum of the other 2. We also looked into the ratio, so what fraction of the overall time accounts for delivering the message, and relative timing differences It's already there for 2 consecutive SMS to account for the variance in the measurements. This is actually the baseline from a previous paper. All of these features can be extracted from a single sender, this time from all 3 senders, from all 3 devices. That means we had all these features 3 times in our data set. In addition, this time we also fused data from multiple senders. Those were simply statistical features, mean, median, standard deviation of pairs of senders of 5 consecutive SMS. We had 3 senders. That means we have 3 pairs of senders. That times 3 features. That makes 9 additional features in our data set. Yeah, the data set then consisted of feature vectors for every SMS. And we used those feature vectors to distinguish different sets of receiving locations to identify the correct one out of the known ones. For classification, we used a multi-layer perceptron neural network. Again, we just took the same implementation as in previous work, and repeatedly trained on fractions of data and tested on the remaining data. We did that multiple times, such that it was cross-validated in the end. And we did this for different types of classifications, for all possible combinations of n receiving locations, with n being 2, 3, and 4. And focus on classification accuracy. That is the share of samples that were samples that were classified correctly. Yeah. And here are the results of that. We are first interested in comparing the individual performances of the different senders under the same condition at the same time, to see how classification accuracy changes between those different locations, and also to assess the results consistency across different sender locations. What we see here is an overall comparison of classifying different sets of 2, 3, and 4 locations for all 3 senders. Each dot here in this plot represents a specific classification. That means a specific receiving device in 2, 3, or 4 specific locations. So that we came up with lots of different classifications overall. First of all, what we see is that the accuracy looks pretty similar for the 3 senders that are represented by different colors here. For example, the left block with sets of 2 locations, the 3 colors represent the 3 senders. But second, we also see that the classification accuracy highly varies. And there are a lot of cases in which it also doesn't really work, because what we also see here are those dashed red lines, and they represent randomly guessing the location. So we see lots of classifications are even well below just guessing, which means that we can't really learn a lot from this when only looking at these numbers. In terms of consistency, we can, however, also look at how a specific classification performs for different senders. In these figures here, we see the x-axis denotes the accuracy achieved by one specific sender, and the y-axis by some other sender. And the closer a classification is on the main diagonal axis, and that means that it has similar performance for both. What we can learn here is that for the two senders in Germany, they are B and D, so the leftmost plot at the bottom. They are fairly similar because they're all arranged mostly along the main diagonal with some minor variations, some a bit better for sender B, some others are a bit better for sender D. The sender in the Netherlands, however, seems to perform a bit better because, well, when looking at the 2 plots to the right, the sender V on the y-axis, because the point clouds tend to be fairly above the main diagonal, which means that for sender V, we have a higher classification accuracy than for the others. Next, we took a look at the performance when combining data from multiple senders. First, we only concatenated the data, so still looked at single sender features and just put them together in one large data set, looking at all individual data at the same time. What we can do here is pairwise comparison for pairs of senders. So I already said we had 3 senders. That makes 3 pairs, BD, BV, and DV. Here we see on the x-axis the maximum accuracy achieved by either of the 2 senders, so when considering only their individual features. And on the y-axis, we see the accuracy when using the combined feature vector, so where we appended the respective data onto one another. And yeah, if a specific classification is on the main diagonal axis, that again means that the combined classification is as good as the best individual one. We can not only do that for pairs of classifications, but also for all 3 locations at the same time. So with all 3 attacker locations at the same time, we can see this on the top right. Again, we compare the combined classification on the y-axis to the best performing out of the 3 individual ones. What can we learn from this? Again, those point clouds seem to be shifted a bit, at least a bit above the main diagonal, which implies that there is a certain improvement when combining the data for the majority of cases. It is important to know that this represents the minimum improvement, since we're comparing against the combined classification against the best one of the individual ones. A single location adversary would not necessarily operate in the best of these 2 or 3 positions, which means that, yeah, we have a lower bound or conservative estimate for the improvement. And another thing is that the majority of classifications is better than random guessing, better than on the slide you've seen earlier, because, again, the chance of random guessing is indicated by those dashed lines in each plot. Yeah, we see that most of the classifications move further on to the top right corner. The last thing is we're now looking at the combined classification, including the multi-sender features. So not only the where we simply appended the individual data, but also with the additional statistical preprocessing. It's, again, the same scheme as on the previous slide. We compare the performances of a combined classification on the y-axis with the maximum of the individual ones on the x-axis. The first plot is here for reference. It is, again, only the combination of the single sender features like it was on the last slide for reference. Plots 2 and 3 then represent combinations with multi-sender features integrated. And when comparing them with the simple concatenation, we see an even higher improvement. So the classifications move further up above the main diagonal and further up towards the top right, which lets us conclude that, yeah, well, combining data from multiple senders first improves identifying the location, improves the attacker's capabilities to infer the location, and using the additional statistical features from the preprocessing also further improves the identification, yeah, over simple concatenations of data. If you're interested in more about this, please read the paper. There's a lot more analysis in it, a lot more detailed analysis. We compare performances between different receiving devices that also played a role. We analyzed the impact of different sample sizes. So how many SMS do I need to achieve that goal? So is it 100 SMS? Is it 1,000 SMS per location? We are also discussing countermeasures that could possibly disable this timing side channel, because well, one could disable or filter silent SMS, which would at least render it unusable for silent SMS. One could maybe randomly delay those delivery reports to make it more complicated, or add some option to make this optional. Because right now, there's nothing to really prevent this on the side of the target. All of these countermeasures that are possible would have to be implemented at the network operator level, because it's part of the standard of SMS. So there's nothing to be done on the user side. And with that, I would like to come to the conclusion and the takeaways. SMS-based location inference is still a stealthy and targeted attack. It's technically quite easy to achieve. You need to be able to send SMS, but operationally it's a bit more challenging because of the amount of SMS you have to send. And operating multiple senders has the potential to improve its effectiveness. You can read our paper, you can have a look at our data and code, which are available on GitHub. You can read last year's USENIX paper, you can read the NDSS paper, in which we already did the same thing with Messenger app. And yeah, with that, I'd like to end my talk. Thank you.